Okay, yeah, my name is Stefan. I'm a freelance developer in Berlin, and I have a project that I develop right now, which is based on Cling and LVM.org. It's an experimental C++ REPL for bare metal devices. And I'm trying to stick with 30 minutes presentation to give room for Q&A afterwards for 20 minutes. If you have short questions, you can interrupt me anytime. Otherwise, please just write them down and ask them during QA. I think we will have enough time then to cover everything. Let's have a short look at the summary. I called the thing Easy Clang. Easy stands for Echtzeit, which is something like real time. It uses C++ and has a few meta commands that you may know from Cling. It physically runs on the connected development board. Not all Cling features work yet, like transaction rollback has some issues, and their like error recovery, well, it will just crash if things don't work. It only works on Linux right now. I'm using Ubuntu 20.04. The firmware is developed with Platform.io and built with GCC right now. And well, the current development mode is go fast and break things. So please bear with me if during the live demo things don't work as expected. That's actually expected that it will happen. I think we will deal with that. Originally, I aimed to do my presentation with the Teensy board. That would be this one here. It does not work as good as I hoped, so I will fall back to the Arduino Due, which is a bit larger. I just wanted to say like this is the kind of board that I wanted to that I'm aiming to cover. Is everybody, by the way, do you see my shared screen and the two devices, just to make sure?
Yes.
Yes.
Great. So we will not do that for now. I hope next time I can show it on the Teensy. For now, we will use the Dewey, and I will just quickly jump into the demo. So I start the JIT on my host computer. Just don't get confused. This is running on Ubuntu. I'm SSHing into the machine, and I use macOS as the user interface. So now we are connected to the Due. It is a ARM non-EAVI target and has a Cortex M3 CPU. There's a serial connection, and now we can type commands here and they will be executed. Let's first load the header for the development board so that we have definitions available. I think I have a little lag in my command line. Let's see how it works. And I include another definition for Arduino built-in functions. With that, we can do something like digital write now, and there is something like a built-in IDE that you see here, the orange one next to the green one, and this, let me check that we have the definition for that. It's called LED built-in. It should have an ID 13, and we have constants like low and high. They're all from Arduino here. So now we can call digital write on the LED and turn it off. So when I execute that, the orange LED here on the board should turn off, hopefully. That works, and we can turn it on by doing the same with high. So now it's on again here. this is kind of the hello world in embedded world. It's called the Blinky example typically. And this is something that I showed in the little teaser that I posted online before. I want to do a little more than that here. So let's include some functions for analog inputs. The board has a number of analog inputs that have IDs again, like A0, for example. Let's check the IDs 54, yes. And with that, we can read analog signals. And for that, I want to introduce my breadboard here. It has a potentiometer, a knob where you can regulate the current coming in and the current that is on this orange wire here. Let's quickly connect this to ground. And let's check first with the LED that you see here that it works. So I connect this to 3.3 volts here. We should now see the LED turning on. Yes, it works. So I can regulate the current going through here. And what I want to demonstrate in the REPL is, let's connect first. When I connect this to the A0 input on the board here, and current again, then we can read out this value from the REPL with the Arduino functions. We first have to set the board's analog digital converter resolution, and the resolution itself, let me show that as well, should be 12 bits, and this means it will be a value between 0 and 4095. So let's do the analog read here. And we get value 0. So when I turn the knob now, we should get a bigger value. And the maximum value, let's see if that works. Great. So that's great. It did not crash yet. That's a good sign. This is like we can define constants and call functions from the REPL here, but we can also load precompiled code. Let me first load a header for a function that is precompiled in a static archive. I loaded the header for the compiler to know the function declaration already. Now I load the archive so the JIT can pull in the definition. And just to show that quickly here, the header looks like this. It defines a printf function, and the implementation looks like that. We use some standard headers. We define some built-in functions that are available in the firmware. And the printf is just a concatenation of these functions, and we use the Arduino VS printf to do the actual work. We could now do things like get the function pointer and signature here. And of course, we could do a hello world now, but it doesn't feel like the world is in a state where we say hello. We probably do something like that. And we get this reported back from the firmware. We can also do things like find string, and string could be ABC, and we get back not only the pointer in this time, but also the string representation. This is a little extension that I did on top of the clang code base. We will have a look a little later how this works. And we could, of course, or let me try. Actually, I did not try that before, but we could dump this string now with printf, and we get back ABC. Great. And we can do that to dump it twice. Oh no. Okay. We of course have to pass the string again. So that works as expected. That's great. A little more complicated example. Let's define a value like this. So from is now value 3, and here's a little for loop that does a countdown. So it counts down from the from value to 0. It does change the built-in LED all the time and print a countdown. You see here, then we'll wait for a bit and go down even more. Great. So if we wanted to define, or if we wanted to change the value like this, that won't work. Clang will tell us there is a definition of from already. So we could do instead, say, okay, let's say it's 5 now. Oh, typo. 5 now. And if we run this again, it will count down from 5 to 0. And the LED should be changing all the time. Yes, great. So that's the minimal demo I wanted to show. We can have a look at the REPL later on. For now, I would continue on the slides and show a bit more about the details, how this all works in the background. Here is the schedule for today. I tried to include as much RPC info as possible, because I think the Cling team also is interested in out-of-process execution, and maybe that can help others to go a bit faster than me. It took me some time to figure out all of that. Starting with the terminology, I see that I have the wrong slides here. Let me fix that quickly. I do have them non-accumulated. Let me use that instead. Sorry for that. Yes, this is how it should be. So first of all, we have a host machine, and then we have a development board. In LLVM, we would call this executor. I will call it device here because, well, I guess it's obvious. On the host machine, we have a command prompt. We have Clang compiler that compiles C++ to bitcode. The JIT engine is based on LLVM org and JIT-link, and the RPC layer will do the communication with the development board. We have some built-in libraries, pre-built libraries. You can, of course, pre-build your own libraries and load them as well, but there will be some of them shipped with the binary distribution. And there is a number of tools to do things like rebooting particular devices that are invoked from the EasyClang environment. The board is connected through a serial connection, and there is a dedicated device firmware, and basically it's a collection of RPC functions and runtime functions, and I will explain that a bit later. The important thing is that, of course, the device is single-threaded, and the host machine has separate thread for receiving messages. So this is a multi-threaded environment. Looking at the hardware dimensions, I think people are quite familiar with things like Raspberry Pi. That's not the microcontrollers I'm targeting. I'm targeting bare metal microcontrollers like the Teensy or sorry, Arduino Due. And a diagram here shows the proportions of the resources available on these boards compared to the Raspberry Pi. Looks a bit like a solar system, and that's intentional because like these devices are a lot smaller than anything that runs an operating system or something. Zooming in to have a better comparison here, The Teensy, like the processor is typically below 100 megahertz, RAM is below 100 kilobytes, and 8 kilobytes should be sufficient. ROM is below, well, 8 kilobytes of ROM should be enough, but right now I'm using the Arduino Dui for development because it's more convenient and debugging is easier and everything. There is something called MicroPython that is you see here in green, and that's something that can be compared with the project I'm working on. MicroPython is a reduced Python dialect that also targets microcontrollers. It ships a subset of Python standard libraries, and this subset depends on the features, like the feature set of the standard library depends on the capacity of the device. So it's different for different devices. On the easy clang side, well, we don't have a complete standard library. GCC has something called new lib instead of glibc, and for C++ there is typically no STL. Open-ended dynamic containers are typically not practical on such small devices. There are partial adaptations like the embedded template library, but I'm not using that right now. In general, we cannot really implement the full standard library because there's no clear standard in, standard out streams, and other things are just not available. So this is quite clear. There's no complete C standard library. The execution model in MicroPython is interpreted, and there is an interpreter on the device, which is really interesting because, well, I don't know if people build a product and want to scale that up and think about there will be an interpreter on the device, then I don't know, but they would probably think we can reduce the hardware size by 90% when we don't have an interpreter. So I'm not so familiar with MicroPython and the environment, but my impression is that it's used for prototyping, and as soon as a product is scaled up, software would be rewritten in C and then distributed on smaller devices. EasyClang is compiled and the toolchain is completely on the host, so there is only a very small stub on the device. The REPL pipeline, by the way, REPL is read, evaluate, print loop, goes through different stages, and I want to show a short overview of what happens one after the other when we press enter in the REPL. So first we'll take the input command, input expression, and compile that to bitcode with clang targeting ARM non-EABI. Then the bitcode is transformed. So for example, local decorations are promoted to the global scope. We would wrap the explicit initializers for the expression into a explicit initializer function that we will later call. There's null checks inserted, so we don't accidentally execute a null pointer or something. And the most important thing here in this presentation is the value reporter that is attached by the engine to the user expression. And you see that on the very right here. This is the thing that will report our result from the device back to the REPL. So this is a synthetic add-on to the expression that we type. This is all very similar in Clang, and we will see the differences in EasyClang on a later slide. Next would be that we commit the bitcode as a LLVM module into the JIT and do a lookup, which does symbol resolution and resource tracking. This is basically unmodified LLVM org, and there is not so much, like, I'm not talking a lot about this. If you have questions about this, watch one of the presentations from Lang, and he explains it very well, how the whole thing works. Of course, the LLVM upstream code is open source. You can also check it out. and try it on your own. The important step for us is the linking step. The whole thing exists as a link graph structure in memory. The LLVM component that does the biggest part of the work is called JIT-link, and it does a few iterations on the link graph, like dead code stripping and external symbol resolution. Symbols can here come from the device firmware. So we send if there is a symbol that we don't know, we ask the device, do you know the symbol? And it may return addresses. Otherwise, we look it up in external archives, for example, the printf archive. And this would then trigger more lookups and pull in more code into the link graph. Once we're done with symbol resolution, we allocate a buffer on the device and get that back base address. We can then resolve relocations to this base address, and we can lay out segments in memory. And for all this, I wrote a custom 32-bit ARM backend specifically for Cortex-M CPUs. So this is in no way complete. It's only covering thumb instructions. There is no ARM 32-bit instruction support at all, because all these Cortex-M devices only run thumb code. Once we are done with the linking, we have kind of a binary blob that we transfer to the device, and it will copy that into RAM. And then we can ask it to execute this code. Execution will run, and our value reporter will come back with the expression result. And then we print that with the cling value formatting. I did some adjustments here as well, but this print cling value, print unpacked cling value is basically what I use for that. All the vertical arrows here are RPC traffic, and this is what we will cover mostly in the presentation. But before we do that, I want to give a short look at the device firmware, just to see the difference between RPC functions and runtime functions. RPC functions are functions on the device that are invoked through RPC calls from the host side. So these functions are not expected to be called from the REPL itself, like not from user expressions, but these are like built-in symbols that the JIT uses to communicate with the device. And one of the functions, one example is the easy clang RPC memory C string functions that you see here. This is the function that JIT will call when it gets back a constant character pointer. And then this will respond with a buffer that contains the string value. So this is the function that gets executed when we were printing the string, when we're defining the string and got the string representation as the result next to the pointer in the live demo. And the important thing here is that these functions expect serialized parameters and return serialized return values. And you can see that here, input begin and input size is the size of the serialized parameter block, and we just decode that manually here. The read address would read the 32-bit address from the input, and then we make sure this is the only argument because we only need a pointer to read the C string. We would inspect that pointer in memory, copy that into the response. We figure out how long the string is and copy it into the response memory, and then we return with a success notification. In EasyClang, all these RPC functions are synchronous. So the host blocks until the device is done because the device is single-threaded and it cannot do more than that. In parallel, in general, org allows also multi-threaded RPC calls, of course. The other kind of functions on the device are runtime functions. EasyClang report value is one of these functions. This is used by the return value synthesis process. So a call to these functions would be inserted at the end of your user expression, and it gets the sequence number and also the blob in memory and the size that should be sent back to the host, and the host will interpret this blob and print the result. They are directly invoked from other functions on the device side. Entry points for call stacks like these are typically EasyClang Rpc execute. That's the function that runs the expression that we type, and or maybe from interrupt handlers. But I have to say there's still problems with interrupt handlers because they are using them also interrupt serial communication, and then I have a problem that I don't get back results because they confuse each other. It's something that I hope to get working as soon as possible, basically. Runtime functions can be bundled in the firmware, they can be defined in the REPL or loaded from precompiled archives. And these functions can also send asynchronous messages back to the host. We saw that in the printf function. Maybe to have another look at this here. So this function, EasyClang report string, will send a message for us that contains this buffer, and the message will be printed out immediately. So this is what gives us the countdown here that we saw in the demo. Some pitfalls are if we want to use built-in functions directly from the REPL. Just because the function is already available as a symbol on the device doesn't mean Clang knows it already. So we always have to declare these functions as well. So user is asked to provide all declarations that are used. Otherwise, we get an error from Clang. I don't know this function, it will say. And we can do that by defining it explicitly, like you see at the bottom here, or we load a header that has the declaration. Going on to RPC messages, there's not a lot. Setup and hang up are kind of special messages. Setup always goes from the device to the host. So when we start EasyClang, it will wait for the setup message and start as soon as it receives it. And hang up can, in principle, be bidirectional and gets confirmed from the other side. Right now, that does not always work. And of course, like if the device crashes, it will send the hang up, but it will not read the confirm. The most important RPC message types are call and result. In principle, they can be bidirectional calls in org. In EasyClang, this is not relevant right now. It will always be the host that sends a call message to the device, and it will be executed there, and the result will always be sent in response and be dispatched on the host. I write dispatch because when we execute a function on the device, we will define a sequence number, and for this sequence number we have to define a response handler on the host. So when we get the result, we will get a sequence number, and with this sequence number we find the response handler, and this is what I mean with this dispatch here. The response handler, for example, will for the value printer example, it will print the value. I extended that with two more message types, report value and report string. Report string basically for the printf example, but it's useful in general. And report value is not really necessary. It could also be just another result message. But it's easy, it's better for debugging, because call will not only be used to execute our expression, but it will also be used to call the function that allocates memory on the device. So call result are generic functions that also that the JIT infrastructure uses. And if we get back a report value, we always know, that's a expression result. And for debugging, that's great, because you can put a breakpoint there, and then you can skip through all the other call result pairs that work before and after. So these are EasyClang extensions. And to show that maybe that's a bit, that's not so obvious from the first look, but I want to try to explain that here on the example of the EasyClang RPC execute. The JIT will call this execute function, and it will send back a result in the end that confirms the end of execution. But this is the result of the RPC execute function. So this will be a error value, which is like either success or error with an error message. It is not the result of the user expression. The result of the user expression is sent by the value reporter that is part of the user code, and it will have a raw data block as a payload. We will see later how this is interpreted into an actual expression that we can read in the REPL. And the report string is completely different. It's an asynchronous info, and whatever C string we receive there, we will directly print to standard out. So this does not go through the response handler mechanism of org. The lifetime of a call result, something like that. We start with a C++ data structure that holds our function parameters. This is serialized through SPS, which is simple packet serialization in upstream LLVM. This is a consistent extensible encoding for C++ types, and it handles endianness for us. This is very important. And then this is wrapped into a wrapper function result, which handles memory management and out-of-band errors, which could be errors in the transport layer, for example. Maybe the device is not there anymore, and there's any other problem during transport. And it provides a C interface as well. Wrapper function result can be very complicated, and I try not to do more with it than necessary. I basically use this as upstream LLVM uses it. And if you have questions about that, please don't ask me too much. I'm happy that it works. Yeah, then transport will take this payload and transform it into a header and a body. The header encodes size, type, handler address, and sequence number. And we transfer this via the serial communication to the device, where we decode it manually and see, okay, it's a call message. So let the call handler do everything else for us. So the call handler will get the argument, memory block, and result buffer, and it will take care of decoding the arguments and writing the results to the result buffer. And then it will encode a result message for it, and this will be sent back basically symmetric to the way we got it there. And in the end, a response handler will be called on the host side. Again, this response is not the result of our expression. It's the response for the EasyClang RPC execute function. In this case, for example, the result will be sent as a separate message with the report value type here, but it basically works the same way. It has a special sequence number and a special response handler, and this will print out the response to standard out. Yes, and there is the EasyClang report value built-in function that does all the message sending logic. So we can give it a memory block, and then it will do all the messaging. I have to hurry up because there's not so much time anymore, but I want to go through this quickly. The return value formatter in process in clang, maybe I can skip that. The point here is that everything happens in one call stack, and the pointers or the information to reach out back into the interpreter is just passed through the code layers, and this requires shared memory. This will not work in an out-of-process setting, or maybe your processes have shared memory. In out-of-process, in EasyClang, the value extractor synthesizers captures the qualified type of the return value as well, but it will synthesize a call to the report value function and add this as a last evaluation step of the expression. And then it installs an asynchronous response handler that will handle the message that is sent. It will construct a clang value from it and use this clang unpacked value printing function to dump the value. This is a asynchronous process, so we need response handlers, memory management, timeouts, and everything. And this has also good side effects. Message passing means we have a good fault isolation. If my device crashes, the REPL still runs. And we don't need shared memory. Challenges are, there's a lot. First of all, the tooling environment for embedded is still quite proprietary, maybe because hardware is still quite proprietary. So choose one of the symbols up here. If you look for an IDE to program your device, you will probably have to use one of them because they are, actually I don't know, but it looks like they are quite device specific. Open source tooling is slowly evolving with Arduino, which is pretty famous, and Platform.io since 2014, which is like, I could not build this without Platform.io. This is really the single and most important project in the space, I think. Proprietary tooling appears still to be quite dominant, like in commercial applications, and this is my feeling. GCC appears to be the dominant open source tool chain. Memory constraints are, of course, a challenge. We want to have the absolute minimum resource consumption, and the LLVM libraries all depend on LLVM support, which is way too big for a microcontroller. This seems to be partially obsolete for the org runtime, but it still uses STL containers that are probably possible, but like now I have my own decoding, encoding on device, so we'll stick with that. RPC messages can be reduced in size. The LLVM names, for example, are very long, so I just shortened them to save space in a static message buffer, and I removed some fields. That was very important. Serial communication is tricky. I did some improvements here, and it works now quite reliable, but not always. Serial communication seems to be operation system dependent. I concentrate on Linux. I think it works on macOS mostly. And with serial communications, interrupts are very complicated, or maybe I just don't know how to use them. And the debugger also corrupts the serial streams. So I had some pretty bad debug sessions with that. One challenge is built-in symbol lookup. If we have no operating system, we have no dynamic linking, and export dynamic will not create a DISM section in the binary. So my workaround for that is to do a relink step and use linker script magic to retain the static symbols. That works pretty well, but there's a lot of room for improvement here. Another problem is that the Clang C++ ABI is not fully compatible with C++. The uint32 standard integer type, for example, is unsigned long int in GCC and unsigned int in Clang. And this will result in a different name mangling. And so some symbols will not be found if they use this type, which is very unfortunate, but I think I can fix this by building the firmware with Clang at some point. Building on upstream org overall is very well, very good. There's a number of very well designed extension points. There's a few downstream changes that I still need, and I think I'll propose some patches for that. The Rpc opcode is a problem because it's used in virtual functions, and I have trouble sending my extended opcodes through the orgchit. Otherwise, these are really details here. My favorite challenge is probably debugging, and this will be very complicated here. First of all, debugging static firmware is great with Platform IO and GDB and OpenOCD through a JTAG SVD device. Some devices don't have a connector for that, and then debugging gets really annoying. Like Teensy LC has no connector. That's why I did not finish debugging yet. The question is how to fix that in the future. I think I could dump relocated objects to disk at some point and sideload them in OpenOCD or the GDB server that is spawned. I don't know if there is a good IPC protocol or if OpenOCD has any way to recognize new, like additional object or additional debug info coming in. I'll have to figure it out. And of course, if the JIT and the debugger don't run on the same machine or virtual machine, then this is going to be complicated. We will see how to do that. If you have feedback, the most important or the most interesting feedback for me is, do you want to try out EasyClang? What would you need to do that? I will probably publish an QEMU device firmware for it, hopefully soon. On the host side, I only have TTY transport for now. I don't know the priority of TCP connections. That would be an interesting feedback, or if there is other protocols that would be relevant. Device side, I use UART right now, but there's other protocols like CAN, SPI, or I2C. I'm looking for something that does not conflict with interrupts, and I wonder if there's a relevant or compatible alternative here. Also, other architectures like RISC-V or AVR would be maybe interesting. Windows support, I don't know if I want to do that. And if there's any specific C++ or meta features, C++ module support or anything, let me know. I mean, if people come to me and say, hey, I want this, then there's more chance that there will be a feature for that soon. Last but not least, outlook for the next weeks. I'll publish a binary distribution soon. In March, reference implementation for firmware with Arduino and one without anything for QEMU, I think. ABI documentation for April 2nd distribution with customizable devices. So if you have a board that you want to use with EasyClang, you could build the firmware your own and use it with the binary distribution. And if EuroLVM happens in 3rd week of May, I will probably propose a presentation there. Well, I have a number of big features that I want to build on this, but let's see if time permits. With that, I want to say thank you. If you are interested in updates, then have a look at GitHub or my Echtzeit dev page or my Twitter channel. Thank you very much. I'm looking forward to your questions.